to share my slides?
আমি না বুঝতে পারি না, একদম মানে শুনতে পারি না কথা, এটা আমার একদম প্রবলেম হয়, যে কারণে আমি অনলাইনগুলো শুনি না, মানে সেইটাও আমি তো বুঝি না, ও কিছু বলেছে না বলেনি সেটাও তো আমি বুঝতে পারি, সেটাই তো প্রবলেম। না তুমি একে এতে আসতে বলে দাও, তোমার এতে কানপুরে ইনভাইট করে দাও টু কাম সামটাইমস, বলে দাও, তুমি বলে দাও। হ্যাঁ,
Hold on. How did the rest of the event?
She organizes these kind of conferences regularly, and I hardly join because it becomes too long and too tiring for me.
Yes, it's long. Can someone tell me how to share my slides so that you can see my slides?
Sir, you can just present now.
I'm বললাম তো, just wait a little, just wait a little.
I know, but I want to get it ready for when everybody's ready, because I'm not seeing how to do it.
Yeah, you can click on
কি
this
চাইছে
present
কি
now
কি
button is there.
তো করে দাও,
Can you hear me, Jack?
Yes, I do hear you. There's the button, but it's gone gray.
না
Like I
দেখো
can't
আবার
click on
করতে
it.
চাইছে, করো, হেল্প করো, ওরা এত দেরি বা করছে কেন আমি এটা বুঝতে পারছি না, করো।
But for me it
Okay,
is
let me-
showing.
জানি না রে বাবা। কি বলবো? You want to share the slides now?
I'd like to make sure that it works. Yes.
No, you can do it, yeah. No
So I
problem.
click present.
We ask him to start. তাই তো? Okay, I think without, we don't wait for Saurabh anymore. So please, কিন্তু, huh? Okay, no. এটা বলতে হবে, ওর সম্পর্কে দু চার কথা বলতে হবে, এটা।
It's having trouble with the sharing.
Jack, maybe I can help you. You can click on
Yeah.
that present now button. Is it coming to you? Is it working?
It was, but then there's an error.
Okay, you can try again.
Yes. I think I have to leave and come back to make it work
I
again.
think so.
Hi, Jack. Hello. Hello, Jack. Good morning. Yeah, so can you please, can you see that? Like in the bottom where you have many options, there is an option which is an up arrow. So
Yes, I see. I keep, yes, and then when I click that, what should I then select?
So you just click there and then share. If you go to that up button, there will be some options on the right topmost corner. Yes.
Yeah.
We can see it now. Yeah.
Now you see, right, but you don't see my slides.
So you
No.
just go to the slide. You just click on that tab.
Can you see it now?
No.
Click
So
on
it's-
that tab. Click on that slides tab.
There's a tab.
You
Just the next tab I can see. Paraconsistent reasoning program maybe.
Oh, no, that's just the program for
Oh,
your,
Okay. So where is your slides?
well, it's on an Adobe Acrobat PDF in the back.
Okay, you can just open that.
Yes. Like if I do this, does it show?
Have you selected entire screen?
Yeah.
Then it should show. I think you have not yet opened it. That slides. Have you opened it?
Yes.
Okay, it is not coming.
I mean, it's not on the browser. It's in a Adobe PDF.
sorry? What?
It's on a PDF.
It's not a PDF. It's the screen is fixed. Only your cursor is moving, but the screen
I know.
is fixed. Where? Yeah. I think it's.
Can you hear me now?
Can you hear me? We can't hear you now. Zach, we can't hear you. Can you hear us? Okay, now can you hear us? Okay, but we can't hear you. We were able to hear you earlier, but now no more.
Did you send the mail? Yuck. Did you send the mail? Yuck. We cannot hear you now. No, we cannot hear you. But before you switched off the computer, we could hear you. But no. Yes, I received your slide now. We are downloading it, no problem. But now the only thing is that we have to hear you. That's all. No, we cannot. So can you log out and in again? Can you log out and log in again? হ্যাঁ 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 বলো তো তোমার ওই 06 এ পাঠাবো তো
Anything? No?
না ঠিক আছে আমি পাঠিয়ে এখান থেকে নিয়ে নিচ্ছি ওকে 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 পাঠিয়ে দিয়েছি চলে গেছে কিন্তু এখান থেকে
Any luck?
Yeah, I can hear
Refresh
you, but it is very low.
How about now?
A little bit louder.
Okay, this is improvement.
Okay.
Can the people there?
Can you please use the headphone?
Oh yes, but that keeps messing it up. All right.
ও
try again.
হেডফোনটা প্রবলেম হচ্ছে কিন্তু এত আস্তে সাউন্ড শোনা যাচ্ছে না। No. উপরটা তো
You are muted. No. No.
এটা ইন্ডিয়া টক।
I think the headphone is creating the trouble. So we have to go without the headphone.
Can you hear me at all?
Yeah, I can hear you.
কোথায় আছে? রাইট ক্লিক করুন। Jack, we are going to share the screen, but we cannot share you. I don't know what we can do.
You can't hear me at all?
A very, very little sound, like it's almost impossible to hear.
Well, what if I get very close?
It's better.
Okay.
Can you speak
All
a
right.
bit?
Yes, if I speak like this, will this be
Yes,
okay?
yes, it's perfect now.
All right. So I turned off my camera because I'm now sitting very, very close to the computer, so I don't want to scare everybody.
But now you are going to share our screen, which contains your slide.
Yes, please do.
Yes. So can you see the slides? Your slide?
Yes, I do.
Yes. So you are going for the full screen, and then you just tell us to control.
Okay, so I'll just say next slide when I need to, okay?
Yes. Perfect. Just a second.
Yes.
Okay.
Okay?
Yes.
All right. I'll begin.
Yes. Please start.
Okay. All right. Thank you, everybody, for your patience. You would think after 4 years since the pandemic, I would have get the hang of this better, but okay. So today I just want to talk to you a little bit about paraconsistent set theory and a few recent developments. It's an honor to be at this workshop, especially in honor of Newton da Costa, and also with the new work coming out of the Calcutta Logic Circle, to just say a little bit about some recent publications in paraconsistent set theory, certainly not everything, just one little avenue. And mostly what I'm going to talk about is methodological questions to do with what conditional we should use for paraconsistent set theory, because a lot hangs on it. So without further ado, I'll get started. So I'm going to talk about, first introduce the problem, and the problem is circles around proofs for Cantor's theorem in paraconsistent set theory. Then I'll talk about how the conditionals work in the problem. We'll have a little digression on meta theory, and then have some open questions at the end. So that's the plan. And if it's not too impossible, I don't mind if I'm interrupted while I'm speaking. If there's something somebody wants to ask before I get to the end, that's okay. Okay, so is this all working now before I keep going?
Yes.
Great. Okay, so next slide. Okay, so just to warm up, I'm sure many of you already know, but once upon a time, there was an original naive set theory as it was practiced by Cantor and Dedekind and Frege, and it was great. The only problem with it is that it could prove everything. The minority response, what we'll call the paraconsistent response, has been one approach to keep the highly inconsistent intuitive axiom, to keep comprehension, and instead to give up classical logic in favor of the paraconsistent one, with the hope that we will still be able to prove quite a lot, maybe even prove more than the classical counterpart, but still not prove too much. Proving everything is certainly too much. And this is an approach that was pioneered by people like Richard Sylvan or Richard Routley, Ross Brady, and others in the Australasian tradition. In some of my own work, in some papers that I published in 2010 and 2012, and then in a book in 2021, I've continued to argue that something like this hope is still a live possibility. And my way of arguing that has been to show that some of the most basic and important results in set theory can indeed be recaptured by a paraconsistent logic. Next slide, please. So just so we're all on the same page, what are we talking about? I'll say that any naive set theory is a system that has the naive comprehension axiom that says that there's a set for any property whatsoever. There's a bit of argument about just how unrestricted the properties can be, but the idea is that pretty much any property determines a set. Mathematically speaking, the naive set theory problem is to find a background logic in which this axiom can be supported, where it's not trivial, it doesn't prove everything, but it can still prove enough. And in some sense, that's the harder thing. It's pretty easy to find a logic in which this is non-trivial. Say the empty logic is an easy example, but there's a problem with the empty logic, it doesn't prove enough. So we need to find some kind of balance. And it turns out to be a very, very, very difficult problem. So mathematically, if you like, the variable to solve for is the arrow. It's the conditional or the biconditional. And we know from decades of work, going back, say, to work by da Costa and Arruda and Meyer and Dunn, that no solution can combine contraction, which that's the axiom of contraction there. If A implies that A implies B, then A implies B. And it can't have both that and modus ponens, which is quite a tall order to fill. So mostly I've been interested, and many have been interested in approaches that keep modus ponens and drop contraction, but there is a minority approach that keeps keeps contraction but drops modus ponens, and that's what I'm going to be focusing on today in a somewhat critical vein. So next slide, please. Okay, so as background, what I'm going to be talking about, in a paper of mine from 2012, I provide a proof of Cantor's theorem, and Cantor's theorem is the claim that the power set of any set is cardinally bigger than the set itself, even when you get to infinite sets. That's where it becomes interesting. I'm going to assume we're all familiar with that. I proved that in the 2012 paper in a new argument using full comprehension and a paraconsistent logic that uses a relevant logic conditional. It doesn't really matter for today what relevant logic is, other than that the conditional obeys modus ponens. And that's in, again, this Australasian tradition of relevant paraconsistent set theory. Next, please. So the recent work that I wanted to address is in a paper published bad, I think, for a paraconsistent set theorist hoping to say something about cardinality, because it turns out then that the size of any set and its power set collapse, and there's really no structure in the transfinite above zero, because this is not even restricted to transfinite numbers. So Peterson appears to have created a problem, and I wanted to talk about that. Next slide, please. Stuff here. Usually I would, right. All right, so what I'm going to argue is that Peterson's claims and results, I think they are trouble for anyone who's interested in LP set theory, and there are such people, but I'm going to say it is not trouble for a system that's based on a more robust paraconsistent logic. The whole trick turns on using a language that has no conditional, as Peterson acknowledges. And what I'm going to try to suggest is that when you use a logic that has no conditional, you can make all sorts of claims that look on their face very scary, like every set is cardinally identical to the size of its power set. But they only look scary because they don't say the same thing as results phrased with a language with a conditional. So really my takeaway today is to urge members of the paraconsistent set theory community that any possibility that we might have still thought for working in LP or related set theories that don't have modus ponens, I think are very limited options going forward. System, a great relief, but I'll say I'm addressing that. I'll also say that the result today is relevant to some of my other work where I've claimed that you can prove classical results in their material conditional form. If what I say today is correct, then some of the more recent work I've done, say in a 20 to the next slide.
Hello, Jack, can you hear us? So we are facing some internet problem. Suddenly your voice is not clearly coming here. So can you please wait for 1 or 2 minutes? We are going to fix it, then we can start again.
I've lost my
Can you please speak?
Hello, I am speaking now.
Yes, yes. Now we can hear you. Yes.
You hear me again?
Correct. Okay.
Okay.
Just a second.
Perhaps this is a sign that somebody doesn't want us to be doing paraconsistent set theory.
Okay. Yes, you can continue now.
I continue? Okay.
Yes.
Okay, very briefly to recap, I'm not going to go through all the details, just to give you the idea. The way you can prove Cantor's theorem using naive comprehension, it's similar to the standard proof, but it uses an extra twist. So you take any set, any non-empty set M, and you see that it contains a diagonal element, which I call Rm. It's the set of all the things that are in M that are not in Rm. So this is a circularly defined set, but that's allowed using full naive comprehension. The important thing to notice about this set is that it's a subset of M. Every member of it is a member of M, so it's a member of the power set. Is the screen being, I can see the screen. Is the screen being presented?
Yes, the screen we can see that where it is written Rm is equal to the set X such that X belongs to M and X doesn't belong to Rm.
Right.
Yes.
So good. Thank you. I was just watching the comments.
Sure.
So Rm is a highly inconsistent object. It's relative to the set M, but for any member of M, it's both in this set and also not in that set, which means that the set is not identical to itself, because extensionality says that if X and Y, if there's something that's in X that's not in Y, then they're not identical, and that is the case for Rm. Everything in M is in it and not in it, so it's not identical to itself, which is a bit funny, but what do you expect from naive comprehension? So what can we do with this? On the next slide, please. So that means if you try to have a mapping onto M, so specifically if you wanted there to be a surjection from M onto its power set or a bijection, you will find that you always miss this diagonal object because it's not even identical to itself, so nothing else is identical to it. So there's never a surjection from the set onto its power set, which is what we need to show. So it uses this object that's inconsistent relative to a set to diagonalize away. So it's a variation on the original proof. All right, next slide, please. So in the paper from last year, Peterson presents a new proof, which is different. His proof proceeds by showing that there's simply one massively inconsistent set, and he uses that to make then a great number of claims. So he finds this single object that's so inconsistent, it proves pretty much anything you want. So let's have a look at that. Next slide, please. So suppose we have P stand for any proven dialetheia, or any contradiction that we've proven. And for example, we would have already proven that the Russell set is a member of itself and not a member of itself. So we have things like that already around. Then we'll have this set, I don't know how to say it out loud. The LaTeX code is top-bot, right? It's like both top and bottom. It's the set of all the things such that a contradiction, a true contradiction, is true. So this is going to have the property that everything is in it because P is true, and also everything is not in it because P is false. So it is also inconsistent with respect to membership, which means that also it is not identical to itself or indeed to anything else. The thing to notice just about this set that's different than the one we saw 2 slides ago is that it's not relative to anything. It's just a gigantically inconsistent set. It doesn't care about M or anybody else. Next slide, please. So what's new is that Peterson manages to show not only is this set very inconsistent and therefore will diagonalize out of any attempted mapping, this set, he claims, also is identical to everything. So we'll see that in a minute. It's a member of every power set, and therefore you can use it to define a bijective function that basically can take any argument and return any arbitrary value. So this set causes a tremendous amount of chaos. All right, next slide, please. So what we want to see is that it's the ubiquitous inconsistency of this set that is really the result that all of Peterson's other claims rely on. The cardinality stuff is actually just a distraction. What Peterson has found is that in LP set theory, there's this monster object that causes not complete triviality, but I think very close to near collapse, and allows you to prove all sorts of things about it. He says these are pieces of bitter fruit, but I think it's probably worse than that. Next slide, please. I'd say in light of the apparently overwhelming inconsistency of this I, it seems like claims about power sets and cardinality are weaker than they need to be. If it's true that almost all sets are identical, or even that there's one set that everything is identical to, pretty much everything is likely to collapse. So this is quite a initially dangerous and scary result for anyone holding out some hope, especially for LP set theory. So let's keep going to the next slide. Can I ask, since we were quite delayed, what time should I aim to finish by?
Jack, I think we can take 15 minutes more. So the original time was 11 to 12. We think that we can go till 12:15 if it is needed.
In working with Da Costa, they tried to consider relaxing, as they call it, separation axioms to have either full comprehension or at least something like Quine's NF. We're in NF omega, which is using Da Costa C systems. They kept, again, running into not complete triviality, not proving that everything is provable, but the almost trivial, or what she calls unpleasant result, that for any x and any y, x is identical to y. It's for people who are already willing to work in a system that appeared to collapse under Frege, and yet we persist. So the fact that it hasn't turned out to be easy doesn't mean that we should give up. All right, let's carry on. Next slide, please. So how does this work? This might be for the logicians. Peter's derivations, working in LP plus set theory, it's nominally addressed to Weber, that's me, and some of my work, but really Peterson's paper is about Priest's logic of paradox LP. So that's what we're going to focus on. So next slide. LP has only, at least the propositional fragment, only has negation, disjunction, and conjunction, which the three together are not enough to define a detachable conditional. You can define the standard material conditional, of course, as not A or B, but then it doesn't obey modus. Assume everybody's familiar with why that's not going to obey modus ponens. So I'm going to refer to this fact as saying that LP has no conditional. Maybe that's overly tendentious or combative to put it that way, but I think it's reasonable and fits with the usage that other people have had. So let's go to, you can, the next slide, but then you can skip the next slide because I just said it, and go to the next slide. So how does Peterson do this? Actually, he works in what looks like a Gensen calculus. He uses Gensen's LK, which is classical logic, but without cut. So you take Gensen's sequent calculus LK and you drop the cut rule, which is essentially the transitivity of the sequent separator. What's neat about this, and what I think is not widely known, is that this is working in such a system is equivalent to Priest's LP. Assuming you're happy to read a translation from the sequent calculus to LP. So if you see a sequent that looks like premises A0 to AN give you B, you just say, well, that actually means that there's a material conditional from A0 AN to B. So we read the sequence as material conditionals. And in the case when there's nothing on the right, that's just translated as not A. And if you have a sequent with nothing on the left, that's just translated as B. And this gives us a straightforward back and forth translation scheme so that you can work in what looks like a sequent calculus, but actually what you're proving is things that are derivable in LP. So that's quite neat and also potentially misleading, right? So for example, on the next slide, you look and say, so if you're working in Gensen's LK and all you've dropped is cut, then don't you have these full negation rules where negation can move something back and forth from right to left as usual? And yes, in this approach, we do have those apparently familiar rules. It's possible then to have a contradiction because we don't have cut. So you wouldn't cut together the last two lines of A, not A, there and get the empty sequent. So the whole system is non-trivial. Some people have complained, for example, Dieker and Pauli in 2019, that this is really just a slightly sneaky way of writing the failure of modus ponens for the material conditional. These look like kind of strong negation rules, but if we read them under the intended translation, what do they say? They say that not A implies not A, and A implies not A, which are both actually much weaker than what it looks like at the top of the screen. So this is partly how the approach is done. Next slide, please. Okay, so we're working in what looks like a Gensen calculus that actually proves things about LP. Peterson then is going to make all kinds of claims about identity. How do we define identity? Well, he's going to define it using the material conditional, which is, I'm going to write it with this wiggly identity to make it clear that it's not necessarily what you should call identity, which says that S and T are identical if everything that's in S is in T and vice versa, where the if in the statement I just made is material, which actually is just a bunch of disjunctions. So I've written it out there. That's just defining away the material conditional. So this is what you would write if you were working in LP set theory, I think. Such a notion is not transitive and does not support substitution. It's potentially confusing. So if we go to the next slide, it is possible to derive sequence that look like the transitivity of identity using this definition. But again, these sequence are not what they usually mean. It's a translation. And if we translate it into the usual LP language, we see that we just have a disjunction. Either A is not materially identical to B, or B is not materially identical to C, or A is identical to C. And that classically is transitivity, but not in the paraconsistent case. Next slide, please. Right, so indeed you can have this sequent be true and be derivable, and you can have A be materially identical to B and B materially identical to C, but it doesn't follow necessarily that A is materially identical to C. And all of this is, and why is that going to be derivable? Well, it's derivable because in LP, all classical tautologies are theorems, at least as sentences. So since there's a sentence that would say that the material conditional is transitive, we'll get a sequent that says that. And it's to say that proving that sets are identical in the sense of this material equivalence doesn't carry the force you expect from identity statements. So Peterson doesn't explicitly derive this, but he could have, and it shows both the apparent power, but also the dangers of working like this. So this gets to the core of Peterson's argument. So we can get to this on the next slide, please. So all of Peterson's stuff about Cantor's theorem comes down to this definition of identity and that highly inconsistent set that we saw a few slides ago, top bot, the set that has everything as a member and also nothing as a member. So everything's in it and not in it. Well, with the material definition of identity, indeed, we can prove that everything is identical to top bot. How would we do that? Well, for any A, since A is in top bot, then just by disjunction introduction, A is in top bot or A is not in T for some arbitrary T. And that says materially that being in T implies being in top bot. Similarly, since A is not in top bot, nothing is, well, then again by disjunction introduction, well, then A is not in top bot, or it's in T for arbitrary T. And now we've got material conditionals going back and forth between anything and this inconsistent object. So it seems straightforward, almost too easy to prove that everything's identical to it. Next slide, please. All right, so if material identity is read as identity, this is very close to triviality because it says something is identical to everything. And the fact that if you have a true contradiction or a dialethia, then it will be materially equivalent to anything has actually been noticed for a while. And this is just the set theoretic expression of that more basic fact that a material biconditional will hold between anything and a true contradiction. But so much the worse, I think, for the material conditional because, next slide, if we phrase the above argument with a relevant conditional and define identity now with full, a conditional that obeys modus ponens, it says that S is identical to T when members of S are members of T and vice versa, then the proof that we just saw obviously no longer works. You can't just do it with disjunction introduction. You'd need to say, well, since A is a member of top bot, then if A is in arbitrary T, it's in top bot. That's using weakening. And then you might say, well, since A is not in top bot, then if it were, then it would be in anything. That's a form of explosion, which is obviously paraconsistently problematic. Or if you wanted to avoid explosion, you could use weakening and then contraposition. and say, since A is not in top bot, then if it were in arbitrary T, it would not be in top bot by weakening, then contrapose, and then you get that I is identical to T for any T. But all three of those steps that are marked there with arrows, none of those are going to be allowable in irrelevant logic. We know combining weakening and contraposition, let alone the use of explosion, will lead to failures of paraconsistency. So this is obviously going to fail. All right, I'm going to start editing a little bit so that I get to the important stuff and not go on for too long. So I think we could skip the next slide. You can come back to that. All right, so if we followed what I've just said, I think it now requires very little spelling out why pointing to problems with a material identity are meant to be problems for irrelevant set theory. It's an ignoratio elenchi. It's missing the point, right? So crucially, if we're talking about Cantor's theorem and power sets, Peterson says the super inconsistent object is in the power set of every non-empty set. Well, how is that going to happen? Well, using just a fragment of the argument we just looked at, since nothing's in it, then nothing's in it, or something's in T. So that proves this material implication. If we're happy to treat that as subset, then yes, it's a member of every subset. But I think this is good evidence why we shouldn't do that. So on the next slide, right? If we agreed to read this material accident as saying that I is a subset of everything, well, that really would cause havoc for subsets. But if instead we agree that a definition of subset using a real conditional as displayed there, then such accidents don't occur because, again, we don't have weakening, we don't have these problematic inferences. So this basically is going to stop Peterson's proof that falsifies Cantor's theorem before it even begins, before we even get to saying anything about cardinality. All of the setup isn't there. So let's see. Yep, so next slide, please.
Jack, I think that S subset T, after arrow, it will be X belongs to T, right? It's a typo, I think. For all X, X belongs to S. Yes.
Yes. So that should be an X. Yes. X in S implies X in T.
Yes.
Thank you.
Yeah.
Good. You're paying attention. Well done.
We all.
All right. So basically, we can say the same things about, for example, if you go and try and talk about functions and what it means to be a function or a surjective function. If we use a material conditional to phrase expressions about functions, like we might say, well, the output of a function is unique. That means that if you input A and the output is B and C, then B must be identical to C. So if you wrote that using material conditional, you'd get something like the statement in the middle of the page there. But I think at this point, it's now clear that in no way forces the output of a function to be unique at all. Indeed, both the premises there could be true without saying anything about the relationship between B and C. So again, on the next slide, I hope there's no typos here. If we compare this with an entirely different expression written with an arrow that says the output is unique, then it will make all of Peterson's claims impossible. Indeed, if you were using this definition of function and then you proved that there's some gigantic object that everything is identical to, and then for any fx is identical to it, well, that would be eschatological. That would be the end of the world, to use an excessively long word. Right? If f is the identity map, then this would just cause the universe to collapse to a point. So in the presence of this object, one definition is trivializing and the other is not. So they clearly mean different things. All right. These expressions, they have different truth conditions, they have different inferential behavior, and they have different consequences. So we can skip a slide, skip the next slide and then, yep. So look, I think Peterson's quite clever in the way he proves things. I think using material definitions like that, it wouldn't be very surprising to learn on his setup, even though he doesn't claim it to be so, that maybe indeed every cardinality or maybe even every set is identical in the sense of identity using material identity. But I think it would be very surprising to learn that this entails that all sets and all cardinalities are actually identical. So to draw some wider lessons about this, if we go to the next slide, we have known for a long time that LP set theory all on its own allows a one-element model of set theory. It doesn't mean that the one-element model is the truth about it, but it's possible to make all the sentences that you want true using a single object. So this has still led to some ingenious work. Priest has some stuff in 2017 showing, riffing on some techniques from Joel Hampkins on how to manipulate models of LP. There's a growing literature on more generally algebra-valued models of set theory that allow controlled selection, and there's a paper by Santiago Jaquich Martinez from 2021, specifically about if we used LP or an algebra for LP as the underlying logic algebra for the model selection, you can do neat stuff with it. And so there's this work by Saurav and collaborators that I recommend looking at very much. And they're not necessarily recommending looking at LP set theory, but it would be a special case of some of this algebra valued work, I think. I just want to urge caution that really there's very little reassurance that LP set theory on its own is not almost completely structureless. It's highly problematic. So, yeah, next slide, please. By the way, I keep saying paraconsistent set theory, but I hope it's clear that there's many different approaches to paraconsistent set theory, and I'm just talking about one particular one, but it's always interesting to see other ones and how they relate to each other, and especially when we discover the same thing from different angles, right? So look, you might say, oh, but Peterson establishes that this is not a one-element model or a one-element set theory because, for example, there's a universal set and an empty set, and you can prove that they are not identical, and indeed that there's an x and a y that are not identical to y. That does not, in fact, show or ensure that there's definitely two objects in the sense of numerically distinct objects. For all we know, that's just a single object there being identical and non-identical to itself, which is unlike the situation in, say, the relevant set theories that I've explored, where there's a universal set and there's an empty set, and if they were identical, then that really would be trivializing. So again, these are all different. Okay, I see I only have a few minutes left. I was going to go on a little tangent about what would happen if you phrased everything in LP, and that's from some notes that Hitoshi and Omori and I have been working on, but I think for the purposes of today, we'll skip over that. So I'm skipping ahead a lot now. Can you skip forward maybe 4 or 5 slides to the one that starts, while there is something interesting to say here?
Okay, so should I stop here or we'll go ahead? 4 or 5 slides?
Can you skip up to slide 45 and I'll just finish? I'll say a few things to finish off.
Okay, you just tell me to stop, then I'll stop.
Okay.
Is that here or go ahead?
No, yep, stop, yes.
Okay.
Okay. So what have we said? Look, it looks like all classical tautologies are theorems of LP, and that can only be done by the sentences not expressing what you might think they express. So if you think that the thing at the top of this slide looks like modus ponens, that's, I think if you take LP seriously, you have to shake that off. So LP has this one element model. It also has models where every single sentence is satisfied. So I heard João Marcos once refer to that as the Dada model of LP, the surrealist model in which everything is satisfiable. No sentence is ruled out, which means that the stuff you can prove in LP is really quite muted in terms of what is ruled in. So on the next slide, please. So for example, it's a theorem of LP that the material phrasing of explosion holds, and that has been known since 1979. If the fact that LP can prove, and if you wrote this, right, using the proposed Gensen translation, it would look like explosion. It would look like you're working in a sequent calculus with explosion. If that means that LP explodes and is in fact not paraconsistent, then all the worse for LP, but it does not, so it's not. So just a few final open questions and remarks. Next slide. I think Peterson's paper, the reason I thought I would tell you about it, is that it does contain some interesting and sustained new ventures into inconsistent set theory, and you don't see a lot of people trying that. And I think thinking about this illuminates some further features of naive set theory. I think what he's shown is evidence that LP all on its own is never going to be a sufficient logic for mathematics. So even if you could get a model, say, an LP model that satisfies all the axioms of ZF and maybe even all the theorems of ZF, I urge extreme caution as to whether that means what it looks like it means. It shows that if key notions are defined materially, you'd be able to prove stuff that is bad. So if we could skip to the next slide, but then to the next slide and say on a self-critical note. So, yep, thank you. So just to be introspective here, none of what I have said says that stronger set theories like relevant set theory or paraconsistent set theories with ponenable conditional trying to work with naive comprehension are free of problems. And there's all sorts of challenges that have not been addressed, and we don't quite know how to address them yet. The set theory in my 2021 book simply omits the development of the theory of cardinal numbers, and there's a reason. It points to some serious challenges with that. It's disturbingly easy to prove inconsistency results in naive comprehension. Not quite as strong as the ones Peterson claims, but you do seem to be able to show that all sets have some inconsistent subset. It's not the same set that's in every subset, but every subset has a certain degree of inconsistency. That allows you to claim that all sets in some sense are Dedekind infinite. I put infinite there in scare quotes because obviously not everything's infinite, I think. It's possible to inject the entire universe into a point. If you start looking at meta theory, it allows you to say all arguments are invalid, which looks very problematic. So all sorts of scary stuff. Next slide. So these more robust paraconsistent systems like LP and like Arruda and da Costa's work, they have non-triviality results. We know that they're not completely trivial, but we actually don't know how close to triviality these naive set theories really come. The object that Peterson identifies, this top bot set, if you accept naive comprehension, it does exist, and it does have all sorts of very virulent properties, very strong properties. I've tried to use it for good rather than evil, but it's an open question to what extent it can be controlled, and we need to know more about the stability of the universe it inhabits. So next slide is the final slide. For all I've said here, as I've speculated about elsewhere, Peterson might be right that Cantor's theorem is, on this type of approach, a dialethia, that it's both true and false, but it just wouldn't be for the sort of cheap, thin reasons that Peterson has given. So more work is needed to understand the supermassive inconsistent object at the center of the set theoretic universe that paraconsistent mathematicians have identified. Just to do that will require that we work with fit-for-purpose tools. Okay, thank you for your attention and for your patience.
Well, there's a time for questions. So, please, anyone? And also the online participants, if you have any question. So, yes, can we go there? Yes, this one, yes. The online participants as well, if anyone wants to ask any question. And from the offline. Well, yes. Okay, so Professor Chakraborty has some questions. So Jack, please. Yeah.
No, this is not questions. Actually, I didn't really realize everything, but I had a feeling of kind of helplessness because so what I think that any of you, I mean maybe yourself or Saurabh or any others, can take a project of writing down in more or less non-technical terms about the various approaches to paraconsistent set theory. That perhaps would be quite helpful at this stage of development. Already, I think about, when was your first paper published, Jack?
2010.
Yeah, so it is now almost 15 years. So I would really like to know, because I didn't know about Peterson's work at all. I knew little bit about LP, your work, initial works, and Saurabh's initial works. But now I think it is high time to make some kind of summary. Summary, not summary, but a narrative of what is the state of affair now in simple language, simpler language, less technical language. Yeah.
I agree that communicating more widely and attracting especially new students and people who find it interesting and are willing to work on it is the way to the future.
Yeah, so also I just want to comment one thing that since it has asked you that when was your first paper published, you said in 2010. I can remember that I started my PhD work by reading that paper of yours, which was published in 2010. So I can remember that Sat gave me that paper and asked that you start from here, and then it was started. I have just one question, Jack. Just I want to know your point of view, like in that Peterson's work, like when you discussed that all cardinalities are same. So if in some model that happens, then which kind of mathematical theories or theorems or results we can expect? Like what you expect?
Well, I think that if you end up with a theory that says all cardinalities are the same, then that's pretty good evidence that something has gone wrong.
Something what I missed? It's evidence of what?
Evidence that something has gone wrong.
Okay.
I think, if you want to do mathematics, that if it turns out that all quantities are the same quantity, there's really very little to do. So I think these are points where even if you say, I'm willing to tolerate some inconsistency, I'm willing to be very open-minded, there still have to be places where we say, no, that's too much, that's too noisy, and there's nothing interesting that we're going to learn from models like that.
Right. Yes, sir, please. One more question, Jack.
No, very simple point. Has there been any approach from the standpoint of category theory towards this philosophy. Or so, in other words, paraconsistency through category. I remember there was one talk in fifth World Congress, somebody from Australia who spoke something. That might help in further understanding of the basic points.
So there's a school in Mexico led by Luis Estrada Gonzalez, who has been interested in category theory and using category theory to understand paraconsistency. So he and his collaborators and students have been doing some interesting work on that. For example, we know that the logic for a topos is intuitionistic logic, and if you dualize the topos, then you get dual logic, which is paraconsistent. And just that as a starting point, they've been doing some work on that. So I would recommend the work from that school as using category theory to help with these things. Yes.
Probably someone has written something on the chat. Oh, the screen is still present, right?
Yes,
Okay.
that was a while.
Yeah. Okay. Is there any other question from the online participants? No, like the offline one? Okay, if not, then we thank Jack for this roller coaster ride of presentation. And we hope that in future we will get you not only on online, but in person as well, in Calcutta Logic Circle mates. Okay, thank you very much. Thank you again. And let's move on to our next talk, which is from Shoma Datta. So Shoma Datta is now currently working in the field of logic in the University of Poland, Warsaw. Sir? Not in, okay, but anyway, so University of Warsaw. Okay. So we invite her for her talk on paraconsistent logic with interderivable notions of consequence and inconsistency. And I think that your talk will be followed by Bidhan's talk. Okay, we are handing over the mic to Shoma.
Okay. Just check that whether they can see it.
So, is the screen visible to the online participants? Can you please confirm, someone?
Yes.
Yeah, that means you can hear us as well. Okay, so let's start the talk.
Okay, so thank you, Saurabh, but I don't know what Saurabh said about me. So yes, this work is basically today. Okay, thank you. This is the point. Okay. This talk, the content of this talk has two parts. The first part, basically, I will be presenting some work from my PhD studies. A little bit of introduction of which Professor Chakraborty has given yesterday during his presentation. As it can be seen from the title, so in the first part, I will try to present interrelation between notion of consequence and inconsistency in the context of paraconsistent logic. And in the second part, so I basically studied during my PhD during my PhD time, I basically studied interrelations, how the relation between consequence and inconsistency can be in the context of paraconsistent logics. And as Professor Chakraborty yesterday mentioned, that we ended up with a kind of a diagram, T diagram, which can, from which we can get different schemes of generating paraconsistent logics. But in this diagram, we managed to, during my work, we managed to only place some existing logic in one of the branch, and the other branch remain empty till the time Bidhan started working with us. And the second part, Bidhan will present, as Professor Chakraborty mentioned, almost all the leaves are filled up now. Bidhan will present in his talk, in the second part, the work which Bidhan did. So as there was a confusion, this is University of Warmia Mazure in Olsztyn, not in Warsaw. It's a city around, like by train, 2.5 hours by train from Warsaw. Okay. So the idea is basically this came up, we started working on this during this time when I think in Calcutta Logic Circle's weekly seminar, Dr. Sanjukta Basu from Rabindra Bharati University, she was presenting some series of lectures on paraconsistent logics. And during the same time, we were also somehow involved in some exploration between different kinds of notion of consequence and inconsistency. Professor Chakraborty has mentioned in other context graded consequence. And suddenly it came to our mind, because we know that in case of classical context, consequence and inconsistency are interderivable or equivalent, in the sense that if we start with the notion of consequence, we can define inconsistency, and also other way, if we start with the notion of inconsistency or consistency, we can define notion of consequence. And this idea, this equivalence works because in classical context we have this equivalence between these two notions, which is negation inconsistency. That means given a set of formula, if from that set of formula some alpha and its negation can be derivable, then we can call it a set negation inconsistent. On the other hand, absolute inconsistency says that given a set of formula, if we can derive everything from this set, then it is absolute inconsistent or trivial. So in classical context, these two notions are equivalent. On the other hand, we know that paraconsistent logic, the basic definition is that from a formula and its negation, not everything follows. So if you have negation in, you are accommodating the idea of negation inconsistency, but rejecting the idea of absolute inconsistency. So the point is, then it came to our mind, how can it be that can we do something in the context of paraconsistent logic? Can we also write down two sets of axiom for consequence and inconsistency in the context of paraconsistent logic, so that it becomes equivalent like in classical context. So for classical context, we know here I have not presented the actual set of axiom by Surma. Surma basically presented not the whole reference is given here, presented the set of axioms in negation implication fragment of a propositional language. But we started with the basic, let's say that we have negation fragment of the propositional language. What are the axioms? Then we fixed this set of axioms taken from Surma's presentation, and the set of axioms for inconsistency. So here we can see that inconsistency is a binary notion, so its set is inconsistent or not, we can, based on the relation. Axiomatized by these axioms, monotonicity and other, I will not go. Last one is explosion or negation inconsistency, whatever. And then we have this theorem. So this is not original set of axioms by Surma. So we took some truncated version and some modification also, because Surma presented consistency axioms. Okay, so then this equivalence theorem, we can see that given the notion of consequence satisfying all these 7 axioms, not 7, sorry, 5 axioms. Then if we define the notion of inconsistency by this way, you can see this is just exactly triviality or absolute inconsistency. Then it will this incons will satisfy these 3 axioms. On the other hand, if we start with the notion of incons, which satisfy these 3 axioms, and we define the notion of consequence, you can see that way the notion of consequence is defined. It says that if X union not alpha is inconsistent, that means alpha is in the consequence of X. So here we consider absolute notion of inconsistency, whereas here we stick to the notion of negation inconsistency. And these 2 notions become equivalent. So the question comes that when this equivalence between negation inconsistency and absolute inconsistency fails, then how we can design consequence and inconsistency in the context of paraconsistent logic. So again, we started with negation fragment of the propositional language initially. Here, at the beginning, I was focusing on the reading different papers, and this is from kite negation from Michael Dunn's paper. Yes. How to check? Can you hear me, online participants?
Yes.
Yes, Kamalika is saying yes. Okay. Yes, Kamalika said. Maybe someone wants to join. Yes. Okay, so we started with this nice diagram of kite negation, where you can see almost all properties of classical negation are listed. This is this context of calling it subminimal negation, minimal negation, intuitionistic negation, and so on is different. I will not go into that. But the point is that here, these properties like contraposition we can see, along with this property, which is negation introduction, represented by this symbol. Oh, sorry. Okay. Negation introduction, negation elimination, and then this is to kind of, okay, intuitionistic negation, whatever. And I have taken also these properties, reasoning by cases, denoted by this symbol. Then we check this, that this property, and it is already written here. So if we take this property, contraposition basically, double negation introduction, then it gives a kind of a explosion. If we take this property, double negation elimination, it will, okay, I should mention that considering that we have a reflexive, monotonic, transitive consequence relation. If we take this property along with double negation elimination, then it will also explode. And also if we have reasoning by cases, it will also explode. So we wanted to drop, design a notion of consequence in the negation fragment of a propositional language, dropping minimum property. So we can see that subminimal is the common one, which is maybe can be considered as the culprit. So we dropped this subminimal property, and then we designed a consequence operator having these axioms. So first 3 are this reflexivity, monotonicity, and cut, then non-explosion, which is required, and the reasoning by cases and double negation. On the other hand, then comes the question that how should we design the notion of inconsistency, knowing that the notion absolute inconsistency is not present, means we don't want to incorporate that. So the question is that, in this context, if we have a set of formulae X, from X, suppose some alpha and negation alpha both follow, So we may call it negation inconsistent, but there may be some beta which does not follow from the set. So how would we address this issue? So we considered that let us relativize this notion that X is consistent with respect to the formula alpha if both alpha and negation alpha follows from it, but if both beta and negation beta do not follow from this set, so the set may not be inconsistent with respect to the formula. So we relativize the notion. So here the axioms, corresponding axioms, again in the negation fragment of the propositional language. So here we have a binary relation. So we call it para-inconsistent binary relation. So you can see quite immediate comparison can be, if we see here, this is kind of a monotonicity. Okay, and then maybe here we have seen that we know that. Okay, so let's go back to this. Sorry, I wanted to say something maybe and maybe. Okay, so we can see that here instead of that we have monotonicity, but with respect to this relativized notion, and this, which is the set of pi on inconsistent sets. So inconsistent sets are like pairs, X union dot alpha alpha, given that alpha is in X. So such pairs, so this is an additional axioms we have taken here. And then rest are little bit, not much difficult to see that how to change this. And then, then in the negation fragment, this paper was, I don't remember, yes, here, this paper was published in 2011 in Logica Universalis. Before also there was one presentation, paper based on that also in 2008. Professor Chakraborty showed this yesterday. And then we proved this equivalence theorem, that these two sets of axioms are equivalent. That theorem for equivalence I will show later, because further this study was extended, which was published in 2015. Which was the proceedings published by Springer after this 5th World Congress on Paraconsistency. And in this paper, we extended this study for other fragment of propositional language, and we did it very systematically. First, we, similar way, we checked all the properties through which explosion can come, and we tried to segregate. First, in the negation conjunction fragment, in the negation conjunction disjunction fragment. So here you can see we have also proof theorem that you can see this is this typical or right or left, and this one property is disjunctive syllogism, which is basically representing, reflecting how negation behaves in presence of disjunction. So we have proved this theorem that we have proved this theorem that in presence of C1 to C4, that means reflexive monotonic transitive consequence with non-explosion, if we take C8, then C10 cannot be there. And vice versa, if we take C10, C8 cannot be there. So clearly we have two branches from this root node having C1 to C7. One branch with C8 and C9, that means introduction, elimination, or left-right rule. Another with left and DS. Then we further extended this branch, all these branches, with respect in the fragment of negation, conjunction, disjunction, conjunction. So conjunction, again, similarly we added. There was a theorem that if we take, it will be, if I take C1 to C4, and then if I take C8, then in presence of C10, it will be explosive. So I cannot take. So C4 will be contradicted, so I cannot take. Okay, so in that sense, okay, then this, in the conjunction further, it is conjunction we took or right or left, and again one property which is together presenting interaction of conjunction and negation together. It's also a kind of an explosion we know, so we call it and explosion. The symbol is different anyway. and explosion. And again, we check that similar way, C11, C1 to C4 along with C11. We cannot take C13 and on the other way. Then again, we have extension of these branches where we have C11, C12 together in one branch, and C11 and C12 and C13 together. So you can see, I will mention about that latter. Then we extend it in the fragment negation, disjunction, conjunction, implication. In this fragment, we have again implication right, which is basically deduction theorem dt, implication left, which is basically MP, modus ponens, and this contraposition. Again, so here we have rather three branches. None of the two cannot be taken to, what was the theorem? I think I have the theorem here. Yeah. In the presence of C1 to C4, if C14 and C15 hold, then C16 does not hold. And similarly, so you cannot take all three together if you want the consequence to be non-explosive. So we have three branches. So that's the way, we extended also the corresponding axioms for this notion para-inconsistent. I will not go into the detail into that because Bidhan has a lot to say, and and then we have this equivalence. You can see the change that here we have the change. So if I have a consequence operator which satisfies C1 to C16, all properties, then if we can construct an relation PI, binary relation in this way that the pair X alpha is in PI if and only if alpha negation alpha is in the consequence of the set X. So basically you can see we have here negation inconsistency. In the earlier case it was absolute. And here we have that on the other way, if I have a relation representing para-inconsistent, I can define a consequence operator as the way it is written here, quite understandable. I will come to this diagram. So this diagram was really very attracting at that time. And when I finished, during my PhD studies, we could manage to do like, I can tell once again, this is the root node, having all 7 axiom in the negation fragment. Then first this negation disjunction fragment, then negation disjunction conjunction fragment, and then negation disjunction conjunction implication, the whole propositional language fragment. And here we can or right or left together. And here or left and DS, disjunctive syllogism together. And here what is interesting, later I recognize that all these divisions we have in one branch for a connective, left and right rule together, in another branch, left rule and one rule which represent interaction of that connective with negation. So that's the way this whole T diagram is developed, and then we managed to show, check that the existing logics like pack of Avron, PI from Diderik Battens, this is CIE, this LFI systems of Joe Marcos, Water Carnelli and all. J3 already we talked about Jaskowski's logic. POS, I remember the paper, but it's by Roman Tuziak, right? Roman Tuziak, and in this paper he was listing some properties of negation, classical negation, and then segregating. And this fragment, there are some, I don't remember exact properties, but this is also, we can place it under this branch. Calculus of antinomies by Asenjo, we can place it under this branch. Logic of paradox here, D2 discursive logic here, but you can see that all these branches remain empty. So this was a really quite generating a kind of a curiosity. If we can, clearly we can have some logics here, if we can, then all will be non-explosive, but none of the existing logic fall under these diagrams. So in this regard, really Bidhan did a good job. So I will pass this to Bidhan.
Thank you.
Mohadi has a question. Yes, that also Bidhan, with Mohadi and Bidhan we have seen. because here because already when we were doing, we knew that there are systems, paraconsistent system, which are like non-reflexive, non-monotonic, non-transitive even. So those are not considered here clearly. And also Bidhan was checking that maybe not necessarily both two rules, one rule. Also remain, if we take one of the rules, such paraconsistent logic can also be, so there can be other T diagrams, of course. Okay. Okay.
Any other question to Shoma? Before we pass on the mic to Bidhan, from the online participants as well. I think someone wants to join also. Okay, any question to her? If not, then we ask Bidhan to continue. So your slide. The same slide.
Yeah, thank you. I am Bidhan Saha, PhD student of Department of Mathematics and Statistics, IIT Kanpur. And I am doing PhD under the guidance of Professor Mohua Banerjee and Shoma Datto. So I am presenting part 2 of this presentation, which is titled some new three-valued paraconsistent logic that satisfying consequence and inconsistency interrelations. Okay, sorry. Yeah, this is a quick outline of my presentation. So we will start by constructing truth table first for those logic by keeping in mind all the properties mentioned in the corresponding branches. Then we will present rules for those logic, and then after that we will present the natural deduction style proof system for those logic. Then we come up to the soundness and completeness for those logic, and we will finally show some future directions. Okay. Okay, this diagram is already has been presented, and in our journey we focused on 3 particular branches, namely B12, B21, and B22, because most of the branches of this diagram is empty there. And today we'll focus on, in particular, B21 branch, because B21 branch, which is highlighted by blue color. The first, and we'll present the logic corresponding these 3 sub-branches. So, okay, so for that, we choose alphabet for these 3 logics as a countable set of propositional variables. The logical connectivity is the same as our classical one, negation, conjunction, disjunction, implication, and parentheses. And set of formulas are defined as the usual way. We consider propositional variables are formula. Then if we consider alpha and beta formula, then it's 4 components like negation alpha, alpha and beta, alpha imply beta, alpha or beta, all these are formulas. But in the entire picture, the connectives, negation and conjunction is considered primitive, but the connective disjunction is definable for all the logics in the branches. But for the other connective implications, which is considered sometimes primitive, sometimes definable. For example, this branch. For example, the logics under the branch B211 and B213, implication connective is considered primitive, but for the other logic it is considered definable. Okay, so this is, okay, so first we construct truth tables by keeping in mind all the properties mentioned in B21 branch, and where it has and right, and and introduction and elimination rules, disjunction and or left. Yes, disjunctive syllogism and on right. And so from this picture, it is clear that this truth table of conjunction has both the properties conjunction right and conjunction left. Then using this connective, we can draw an order relation on the truth value set and usual way, that if we consider 2 truth value x and y, then x and x is related to y if and only if x and y equal to x. And we get this relation where f is less than t less than u. And here in this picture, we consider both t and u as a designated set. And one thing I mentioned that all these truth tables are matches to the Sobochitsky logic. Okay, so next we will present the truth tables for this connective. So first I will present the truth tables. The left-hand truth tables is for the logic under the branch B211, where DT and MP present, but the property C16, I mean the contraposition is absent. And the right-hand truth table is for the logic in the branch B212, where DT is absent, but MP and C16 all are present. Okay. And interestingly, all these, here T and F, the classical truth values, like true and false, and they behave classically in both the logic. These two truth tables are different in one cases. This is highlighted by this blue color. Okay, but for the other logic, I mean for the other branches like B213, it is quite strange. Let me, and where the boundary condition, I mean truth value T and F does not behave classically in that logic. So I'm telling you, so why we had taken this kind of implication for this logic. So before going to present here that, I would recall the properties mentioned in the branch. So in the branch 213, DT and C16 is present. I mean deduction theorem and contraposition is present, but modus ponens is absent. Okay, now we constructing the truth tables for this connective implication in this logic. Okay, here D represent the truth table, designated truth value, maybe T, maybe U. Okay, since in this logic deduction theorem is present, then all these four positions should be filled by designated value. So we are not, right now we are not fixing what is the exact truth value, but it should be designated one, okay? Then, and this logic has contrapositions. So that means if we take two truth value, x and y, if x arrow y is designated, then negation y arrow negation x should be designated. So then the truth table becomes this one. Okay, so till now we have two empty spaces, and if in that position, if we consider T arrow F is F, then modus ponens will hold. But we don't have modus ponens in our logic. So definitely this space should be filled by designated one. And finally, we take this truth table for our logic. And interestingly, all the truth tables in this table are designated. So that means if, I mean, any propositional, any formula of the form alpha arrow beta are valid there. So, so for that reason, we are saying that this logic is quite strange. Yeah. Okay, so so far we have constructed the semantics part. I mean that all the truth tables for all these three logic under B21 branches. So now the definition of semantic consequence is defined as the usual way. The valuation is a map between the truth values formula to truth valued set that satisfy all these conditions. And based on this semantic definition, the semantic consequence relation is also is a similar way that alpha is semantic consequence of gamma if and only under all valuation V, if truth value of all elements of gamma under valuation V is designated, then truth value of alpha under the same valuation should be designated. And it is very clear, I mean, it is very trivial to see that if we consider two distinct propositional variables P and Q, and this truth table, it is very clear that Q is not the semantic consequence of P and not P. That means all these three logic does not satisfy ECQ. That means all these three logics will be paraconsistent. And the second example ensured us that or right, I mean, or elimination or introduction doesn't hold there. But third example is entails us that deduction theorem will be present. Disjunctive syllogism will hold there. Yeah. Okay, so now we move toward the proof system of all this logic, and all this logic, and we adapt natural deduction style proof system for this logic. Okay, so these 5 rules are considered common to all logics under the branch, and which is denoted by RC, and the logic is of the form, the upper part of this rule, all the branches of the tree diagram, yes. Upper part of each rule is called the premise, and the lower part is called conclusion. And if the premise part of a rule is empty, then the rule is called axiomatic rule. So for first one, the first rule is our axiomatic rule, which is known as excluded middle. The rule 2 is represents double negation introduction, double negation elimination respectively. Rules 3 and 5 represents conjunction elimination, disjunction elimination, and 5 represent the De Morgan. Okay, and these 5 rules are also considered common to all logics under the branch B21. So not for all logics. In particular, these 3 logics under the branch B21. So that means these 10 rules are considered common to all 3 logics under the branch B21. Okay, and these rules are involved, so only negation, conjunction, disjunction involved. So right now, we have no rule for implication part. So now I am introducing the entire, complete set of rules for those 3 logic. These 3 rules, along with above 10 rules, is the complete set of rules for the logic under the branch B211. Where the 3 is very clear that it is represents the modus ponens. And here, we need not to impose any kind of rule involving implication, because in this logic, implication is definable connective, not primitive. So above 10 rules is enough for this logic under the branch B212. It's a kind of rule involving, so not only involving implication, it's involving with so yes, but it's alpha is not definable in terms of negation and or, by the way. It's, yeah. Yeah. It is not expressible by the other. Yes, yes. Classically, it's. So that property also holds separate. Yes, yes, separate. This is a kind of contradiction. So, so not only contradiction, the contradiction along with some formula, if we consider, then another kind of contradiction will be we will get, which is of this typical form.
And alpha. And the negation of alpha beta both, right? You have taken phi and negation phi both.
Mm-hmm.
Like, which is derived, you see that you have written that alpha arrow beta and its negation as well.
Mm-hmm.
So I'm just asking that in rule 2 that you have already allowed some formula and its negation both, right?
But
So the paraconsistency is entered from there. So
But
the explosion is not, of course, but
yes, and explosion is not present there.
no, but I'm asking that, of course, we understand that from here it follows everything. That part is not present, that's true. But we are allowing some formula and its negation together as truth. So in other sense, it is a like the contradiction we are.
So then we combine these two separate rule together. Now we have that beta and not beta and alpha. It will allow another form of contradiction, but the form is not like alpha and not alpha, gamma and not gamma. It is like alpha and beta and not alpha and gamma and not gamma. It is gamma and not gamma. Alpha and beta and not a particular form in alpha and beta. Any gamma can be the gamma.
Yes. No, I don't know about this method. Okay. And for the other, for our strange logic, these three rules are considered along with above 10 rules. But the first one is quite strange, like that every formula of the form alpha arrow beta will be theorem in this logic. And in object language, it's kind of trivial. I mean, so from R213, which one?
From alpha and not beta, you will get not of alpha and arrow beta.
2.
1 1. Roman 1 or the second rule, the last.
R211.
In R211,
Uh-huh.
the first rule, the converse of first rule also holds or not?
So actually we did not check whether it is not, but we can easily check that from the definition of using the truth tables. No. Which one? No.
You check in R213, you check the third rule. You check the third rule of R213. This is just what Jantuda asked, the converse of that.
I'm not getting your point. The converse of this theorem is holds or not.
It holds in
Ah,
R213.
ah. Yes. Mm-hmm. Mm-hmm. This are you talking about this rule, right? Huh? Acha, in here. So actually, mm, I did not check the which were holds or not, but hmm. So, but one can easily check by the semantic consequence relations. Is not very difficult job. Yes, it's can very easily. Okay, yeah. So this the rule is quite strange. It's a kind of I mean explosion. So in the sense that whatever so any formula from any formula can imply any formula. I mean. This is true for all alpha beta. So this is a kind of trivial rules here. But one thing, it's on object level, but in meta level, it doesn't hold that every beta can be derived from every alpha. It's not, will not hold. But here, alpha imply beta should hold for all alpha beta. This is the slight difference between this meta level and object level. And it is clear from this picture that the rule, set of rules R212 is included in others two rules. Yeah. Okay, so now here we present the natural deduction style. The derivation is as like our okay, the syntactic consequence as is already the proof today. Okay, and here the definition tells us that if we consider two logics L1 and L2 with the same language, then L1 is the sublogic is said to be sublogic of L2 if it satisfies that if alpha is derivable from gamma in L1, then alpha is the derivable of gamma in L2 as well. So, and based on this definition and our this observation, we can argue that L21 is a sublogic of other 21. Yes, like embedding.
In 213, can you please go back to the previous slide? Yes, in 213, do you have modus ponens as well?
No, we don't have modus ponens.
Do not have modus
no,
ponens.
No.
Okay. Right. Achha. Okay, okay. We can discuss later.
Okay. Okay, so now we prove is soundness. Soundness is quite trivial. It is enough to show that all these logics, all the rules of these corresponding logics are valid. But the difficult part is prove the converse of the soundness, I mean completeness, and which state that if alpha is semantic consequence of gamma, then alpha will be the syntactic consequence of gamma. So, okay, so for that, we took help of the notion of non-trivial prime theory. What is non-trivial prime theory? A set of formula is said to be non-trivial prime theory if it satisfies all these three conditions. The first ones tell that whatever can be derived from gamma should be belongs to gamma. Second one is non-trivial. That means there is some formula that does not follow from gamma. And the prime condition, this is important condition, and which tells us that if a formula of the form alpha or beta belongs to gamma, then either of the components should belongs to gamma. Okay, and based on this prime theory, we proposed this, we defined this lemma, and which state that if alpha is not a syntactic, syntactic consequence of gamma, then there is a non-trivial prime theory, gamma star, that contains gamma but does not contain alpha. And here we will show that alpha is not the semantic consequence of gamma. So this is our goal. So to prove this, we define a model, which is sometimes called the canonical model, from based on this non-trivial prime theory gamma star. By this following condition, following definition, it tells us that this definitions takes the truth value for a arbitrary formula psi t when psi belongs to gamma star, but its negation does not. It takes the value u if this formula psi and its negation both belongs to gamma star, and it takes the value f if psi belongs to gamma star, but its negation does not. And we showed that this definition, this valuation function, this function satisfy all the condition of the valuation, which I mentioned earlier. So this has become valuations. Okay. So now observe that this valuation takes the value designated for all the element which contain in gamma star. And since gamma subset of gamma star, that means all element of gamma belongs to gamma star. That means truth value under this valuation function is designated for all the truth table, all the formula contained in gamma. But alpha is not there. So that means truth value of alpha under this valuation is not designated. So from this picture, it is clear that alpha is not a semantic consequence of gamma. Okay, so that means if a formula is semantic consequence of gamma, then it should be syntactic consequence of gamma. So hence the proof, the completeness theorem. And these three logics, say here I present, three logics under this branch. Okay, so for the other two sub-branch like B12 and B22, we are not presenting all the detailed things, but just I am showing what are the exact truth tables and their corresponding rules are there. So this is truth table for common to all three logics under the branch B22. And these are the truth tables for implications, corresponding logics. Yeah, so it's implication, okay. So for the B22 branch, we need and explosion, right? Yes, we need and explosions. And this cross diagonal is all these three F, that it ensures us that the X and explosion is present there. And the truth table of OR is its disjunctive syllogism holds, but OR right does not hold, which is from this U or F is F. So from this angle, we can say that OR right doesn't hold. And these are the truth tables for implication for respective logics, where okay, so the first one is on the logic where DT and MP both exist. The second one is for the logic where DT is absent, and the third one is where MP is absent. And yeah, these are the rules, common rules for all three. Yes, yes. And these are the rules for these 11 rules we took for common rules for all the branches under B22. And these are the rules for, complete set of rules for those logics. And this is also the logic under this branch B223 is also the same. Actually, the connective, implication connective is similar to an earlier one. Okay, this is to a connective for the other branch, other sub-branch B12, where implication, and explosion will hold, but disjunction doesn't hold there. Here, disjunctive syllogism doesn't hold there, but disjunction, elimination, disjunction, introduction will hold here. Similarly, here implication, two-tabular implications for respective logics is present. And these are the rules for we consider for the logic under the branch B12. These are the complete set of rules. But in here the implication is considered definable function in that logic. Sorry. Okay. So before going to finish, I am showing you something. Okay, so from this figure, from this rule, it's quite important in the sense that, so these logics are not explosive, but there are kind of explosion there. In those logic, there are some particular set of formulas which are trivial. And so based on these observations, we generalized, we define a generalized notion of gentle explosion. So so in our LFI system, we don't have explosion, but have a kind of explosion, which is called gentle explosion. This definition is here that state that there is some formula alpha and beta such that, in LFI there is an primitive connective, it's called the consistency. And this definition tells us that if a formula alpha together with this consistency of alpha is not trivial, but together with, if we consider alpha and not alpha together with the consistency of alpha, then it is become trivial. And so keeping this mind, this scenario, we define the similar definition called generalized gentle explosion. But here, which tells us that there is some formula. So in the LFI system, this consistency, this operator, this can be considered as an operator. And this is the set of formulas that depend on only alpha. But here we consider the similar operator star of alpha beta, where this depends on both alpha and beta. And if we consider this set together with individual formulas between among alpha not alpha, beta not beta, they are not explosive. But if we consider both alpha beta together with this particular star of alpha beta set, then it will be explosive. So it's quite similar LFI system, and we named all those logic is generalized LFI system. And in particular, in our system, if beta is matches to the alpha, then it's become LFI system, we can argue. So this is the not only LFI system, all the logic under the branch B212 and B22 are all generalized LFI system. They becomes. Yeah, and finally, these are all the logic we got for this one, right? So actually, this is filled by the logic RM3. Actually, you mentioned in your paper, but somewhere there is some typo, but you did not fill that branch, but it is there. Okay, these are our full diagram. Some references that I am using this presentation. So first one is related to the diagram. And the second one is related to our, from where we get the motivation of, to prove the completeness theorem. And yeah. Thank you.
If any quick question from the online participant, the offline participant, we can discuss over the lunch. Any question from anyone from the online participants, if you want? A quick question? Well, okay, if not, then we may end our session here, and we can try to come back by 2. So we are taking 45 minutes. We are trying to come back by 2, and then by 2:05 we want to. Okay, then we are trying to come back by 2. So let's start our next session at 2. Okay.
Hello, do you hear me?
Angana, do you have any question?
Yes, I have a question. Actually, I joined in the middle of this talk, so I don't know whether it's okay to ask. Just a quick question, that is, paraconsistency is basically non-explosive. That's the main departure from classical logic. So how can this be explosive in some way? So I would like to get the answer from quite a different perspective, like less technical, more philosophical. That would be easier for me to understand. Thank you.
No. Yeah, all the logics are not explosive.
Perhaps was saying that in some sense, yes, but there are different logics, existing paraconsistent logic, which relaxes some form of explosion, which allows some form of explosion and restricts some form of explosions. So generally it's the idea that in classical logic, whenever you have a formula and its negation, it will explode. But there are different paraconsistent logic, strict and weak in some sense, where some form of explosion is allowed, or in some cases no form of explosion is allowed, so it is fine.
Okay, thank you.
Some form of explosion is allowed. Weak explosion, that is what I said, weak and strong, I said.
Thank you.
Angana, are you there?
Yes, sir, I'm here.
Actually, your question is, I mean, the answer, proper answer should be that in any of these logics, there is the classical explosion is not present.
Yes.
They have used something called weak explosion, or ki jano namta boleche? Gentle explosion, or there is a notion called gentle explosion, which is not explosion really, but maybe some form of. That is why they should be considered within the classical, within paraconsistency, the ambit of paraconsistent logics. Do you get my point?
Okay, sir. Okay. Then I will go through this notion, because this is very new
that
to
will
me.
Might help you. Might help you. Yeah.
Okay, sir. Thank you so much.
Okay, so we end our session here, and we resume at 2:45 minutes from now.